So I want to welcome you, and the first thing I'd like to do is go over the purpose of the meeting. So we actually have three things we want to cover today. The first is the fact that the city is evaluating their current water supplies. As we all know, there's a significant drought in Santa Barbara and the rest of the state and much of the Southwest. And there's two feasibility studies, again, desal intakes and potable reuse. So the purpose of the technical advisory panel is to look at technical and scientific questions associated with the feasibility studies. So the studies are being conducted by the city's project team led by Corollo Engineering. And of course, there are regulatory and permitting requirements for things like potable reuse. So the technical advisory panel is administered by National Water Research Institute, and there is going to be a public meeting component here where the public can provide comments and questions to the panel. So just briefly about NWRI. We're a nonprofit, a 501c nonprofit. We're located in Fountain Valley, California. We were founded in 1991. We have water and wastewater agency members. And the purpose is to really collaborate on research projects, addressing technical and scientific questions associated with water and water supplies and water resources. So in terms of our agenda today, we want to go over the panel process briefly. But we're going to get a presentation on the design and the initial screening analysis for the potable reuse alternatives in the feasibility study. There will be this opportunity for public comment to the technical advisory panel. And we'll have a brief summary of wrap-up and next steps. So I do want to mention there are resources. There are handouts in the back related to the topic, but everything that is provided today is also up on a web page where you can go and download all the materials. And here's the web page. Suzanne Fauble of NWRI. She can also be contacted for questions. So I just briefly want to go over introduction so you know who's here, who's on the panel, and who's on the project team. So again, I'm Jeff Mosier with National Water Research Institute, and I'd like to have the panel members go next and briefly introduce themselves and tell us who they're with.
So I'm Amy Childress, the panel chair. I'm professor and director of environmental engineering at USC. And for the last 20 years, I've studied membrane materials, processes, and systems for potable reuse and desalination.
Hi, I'm Eric Ziggis. I work for Environmental Science Associates out of San Francisco. I've been working in the water industry for a little over 30 years, started out in hydroelectric and then moved into water supply planning. For the last 10 years, I've been working on desalination projects in Monterey specifically, California American, and working for the California Public Utilities Commission, also doing a little bit of work on indirect potable reuse. My focus in this panel is really on the process orientation and getting us from point A to point B.
Hi, I'm Mike Wayner. I'm Assistant General Manager with Orange County Water District. We do large-scale potable reuse, indirect potable reuse with groundwater replenishment with recycled water, highly purified recycled water. And I've been involved in water quality investigations, water quality management for a little over 40 years, 20 years with the Health Department, Orange County Health Department, and the last 25 years with the Orange County Water District.
I'm Martin Feeney. I'm a hydrogeologist. I've been working in the groundwater and desalination industry for the last 30 years. Currently working on, as part of a review panel for the intake for Monterey's desal plant. Also worked on the intake for the San City plant. Did some of the geotechnical work for the original desal plant here in Santa Barbara. And excuse me? Marina Coast. And Marina Coast, yeah.
Hi, good morning. I'm Heidi Luckenbach. I work for the City of Santa Cruz in their water department. I'm the Deputy Director of Engineering. I have 20 years of experience doing water supply planning, and for the last 10 years working on the City of Santa Cruz's desalination project. And now more recently we're working on looking at some similar projects in terms of beneficial use of recycled water and various ASR projects as well.
Thank you very much, and thank you for taking the time for being on the panel and providing your services. So, Joshua, I wanted to turn over you just to introduce any city staff that's working on the effort.
Joshua Hagmark, Water Resources Manager. We had several staff here. Kathy Taylor, our Water System Manager, and Bob Roebuck, a Project Manager. And we...
Great. And Tom Secord from Corollo, if you can introduce the project team, that would be great.
Tom Secord with Corollo Engineers. I'm the project manager for this project. Here today with Eric Cheresia, our project engineer, who's going to be presenting. Wanted to also acknowledge our sub-consultant team, Dudak, here today, Joe Monaco and Austin Mulcher. GSI, who's helped with the hydrologic analysis, Jeff Berry and Tim Thompson, and as well the USGS staff has helped our project team with the numeric modeling required for the indirect potable reuse analysis that we'll be talking about.
Great, thank you.
Thanks.
Next. Okay, so just in terms of the panel process, it's a little bit unique, but it has a very good way of being able to do a couple different things. One, to get another set of eyes, but also get some input from people who have seen these types of issues in other places or have researched some of the topics. So it's a good way to sort of validate what the project is or the project objectives. So typically, most of the questions, issues we address are scientific and technical in nature, so feedback is given on that. But of course, a lot of things relate to regulations, and so where that intersection of science and policy come together. And typically in projects such as potable reuse, there are specific questions related to water quality or treatment technologies. We do have regulations for potable reuse, but there's also some potable reuse regulations that are being worked on today by the state. And then another thing that's useful about the panel process is they document their feedback, their input in a report. So the panel will develop a report in response to today's meeting, and that will be made public. It'll be submitted to the project team and the city. So we do assist in interactions with the public, such as this public meeting, and with regulators and decision makers or managers in the city as needed. And so I want to move on to agenda item 3, and this is where we're going to hear from the city as well as the project team on the draft report that has been reviewed by the panel. So Joshua, I believe you're going to come up first. Is that correct?
Madam Chair, Joshua Hagmark, Water Resources Manager. We have a roughly 60 slides for you today, trying to summarize as concisely as we can the data that is put together as part of TM3. We are going to start off with doing a little summary of the background and objectives of the study, just a kind of a reminder of how this fits into to the bigger picture here of looking at both subsurface and potable reuse. We're going to provide a little summary on the subsurface intake feasibility and then dive into our potable reuse study. So how this got kicked off in September of 2014 at a meeting with our city council. They were interested in, as a part of reactivation of the desal facility, having us study what it would take, feasibility, cost, and timeline associated with converting the offshore facility to a subsurface intake and look at the options for potable reuse. This is kind of what kicked off the discussion and ultimately became part of our requirements under our regional board amendment. Permit amendment. This scope identifies feasible alternatives, however, is not determining the most feasible or best alternative. We see this information as being extremely helpful in our long-term water supply planning. And so, irregardless of where we end with this feasibility work, the information that we gathered is going to be invaluable when it comes to us updating our long-term water supply plan, which we will have to do. This drought has been, as you all know, record-breaking, and has established for this region of California a new drought of record. So that means we need to go back and look at all of our supplies, and at that time, identify what the need is. What is the supply that we're looking to make up, and with it, the alternatives and data that has been generated as part of this feasibility study will basically be fed into that. The work plan objectives establish the process, and we do have a little schedule here of the work plan. So when we went through the work plan, and there were 7 sections to it, I'm not going to go through all those right now, but the point being that we wanted to make sure that we had a fully vetted public process for getting input on this, and ultimately it was approved by the regional board staff and has basically formed the framework for the feasibility study. Our workshop number 1, which was creation of the work plan, was completed in August of 2015. Workshop number 2 in January of 2016. Today's workshop number 3, and we do not believe at this time there will be a need for workshop number 4. And then we now have a date with the regional board to provide them a summary, basically, of all the information that we've completed here. And that is now May 11th and 12th. And unfortunately, we couldn't get that in Santa Barbara. It's going to be in San Luis Obispo. But so just wanted to recap on where we were with workshop number 2. On January 27th, we held that public workshop. We continued to take public comments up until February 11th. We went ahead and responded to all of those comments and put that together on the NWRI website and made that publicly available. And then the technical advisory panel went above and beyond and also responded to the public's comments, and that was posted to the website on May 12th. And the final report, with all of the comments incorporated, was posted on October 11th, 2016. Take over here.
Okay. Madam Chair, Tom Secord with Corollo Engineers. So I'm going to talk about now our current purpose of the meeting, the Potable Reuse Feasibility Study. We've produced 3 draft technical memoranda that have been distributed to the Project Advisory Committee and also posted to the public website, TMs 1, 2, and 3. We're going to present our time here today going through this type of material. TM1 provides study goals and approach information. It talks about the regional board and the city council requirements, which we're evaluating alternatives to desalination using the existing desal plants screened open ocean intake. As outlined in the work plan, this first involves evaluating the technical feasibility. That's the bulk of our presentation today in Tech Memo 3. For any of the alternatives that survive the initial screening process with that technical feasibility evaluation, we would then evaluate social, economic, and environmental feasibility for these technically feasible alternatives. Unfortunately, none of the alternatives survived that technical screening, so we still have, however, identified what the maximum feasible capacities are, and that information is going to be very useful for the city as the city moves forward to develop their long-term water supply plan update with an understanding of these maximum yields. So moving on to Tech Memo 2, regulatory screening. Tech Memo 2 presents the regulatory and permitting requirements associated with potable reuse alternatives. I wanted to first we have a lot of acronyms on these slides, and there is an acronym handout in the back of the room if anybody would like to pick that up. We do try and identify those acronyms in these presentations, but knowing that we're probably going to blow past several of them, I recommend picking up that handout. Anyway, in Tech Memo 2, we identify the major permitting agencies. As well, we discuss the two types of potable reuse, and those are indirect potable reuse, IPR, and direct potable reuse, DPR. With the indirect potable reuse alternatives, this is basically advanced treating the wastewater, ATW, advanced treated water, and introducing that into an environmental buffer, such as a surface water body or a groundwater aquifer. This type of potable reuse is regulated by Title 22, and Title 22 calls this groundwater replenishment, GWR, and it refers to it as surface spreading. So the next type of groundwater replenishment is subsurface application, and that's using injection wells. With the direct potable reuse that we talk about in this study, there are two types. There is raw water, that's the RW, supply augmentation. That's introducing the advanced treated water into upstream of a drinking water treatment facility without an environmental buffer. So that's the direct and the indirect part. So the direct potable reuse, indirect potable reuse has an environmental buffer, such as travel time in a reservoir or in a groundwater body. So here we have no environmental buffer, and it's introduced upstream of a drinking water facility. The next type of direct potable reuse is introducing the water directly into the potable water system. So here the advanced water treatment facility would be permitted as a drinking water plant. There are currently no regulations in California for direct potable reuse. The state board has, however, recently issued guidelines or recommendations for regulations how to regulate direct potable reuse. But still, to this point, there are no regulations governing direct potable reuse. Wanted to highlight briefly some requirements for IPR treatment requirements that are stated in Title 22. And here we break them up again by the type of application. So groundwater replenishment by surface application. At minimum, it requires tertiary treatment. And that's this top process flow diagram where there would be secondary effluent coming off the wastewater plant would be filtered and disinfected before being sent to the surface application, like a spreading basin. The next type would be subsurface application, groundwater replenishment by subsurface application, and that requires what's referred to as full advanced treatment, FAT. And that involves treating the secondary effluent coming off the wastewater plant using membrane filtration, ultrafiltration, reverse osmosis, and then an advanced oxidation process. So significant with the indirect potable reuse, as I mentioned before, is this concept of travel time. And that the travel time requirement varies by application, so surface application or subsurface application, and then also by the calculation method that's used. So this table is showing the minimum travel time required for groundwater replenishment by the application, so surface application, subsurface application, and surface application using tertiary water, surface application using advanced treated water through the FAT process, or subsurface application, which requires the FAT. So the travel time requirements, they're at minimum 2 months of travel time for indirect potable reuse using the FAT process. With surface application, it's as much as 6 months. And then there are different types of tracers that are used to demonstrate this. There are calculation methods that can be used. This Darcy's formula is probably the lower reliability in terms of what the answer is. This tracer is an actual demonstration compared to a empirical calculation method. What we've done for this study is we used a complex numerical model that the USGS has been working on for the city for a number of years. And so with this method, we have to demonstrate 4 months of travel time for the full advanced treated wastewater using the surface application or subsurface application. So as we said, the regulatory status for direct potable reuse continues to evolve. California has just not adopted any standards for this yet. The guidelines have been published and are a starting point that we use to inform this study. Direct potable reuse projects will likely incorporate, so this term log reduction in excess of Title 22 requirements. Log reduction, for the lay people in the audience, it's reducing a concentration by a factor of 10 each time you treat. So 14 log would be basically 14 factors of 10 reduction of enteric virus, 10 log reduction of Giardia, and 10 log reduction of Cryptosporidium. So the direct potable reuse projects will likely be required to incorporate additional treatment barriers for trace pollutants, as well as enhanced monitoring for the pathogen removal and also these trace contaminants. Because there is no environmental buffer, there's going to be an engineered storage requirement that allow each key process to be monitored so that the quality can be verified before distribution. So the engineered storage time will be based upon this failure response time. How long does it take to analyze for the contaminant, and how long does it take to respond to notification of that failure? So that's how the engineered storage will be designed. So moving on past this technical feasibility screening, and there's actually some other requirements that come in through the regulations in terms of permitting documents, engineering reports, report of waste discharge requirements. There's an environmental review process. The city would need to update their long-term water supply plan and its programmatic EIR. As well, there are a lot of regulatory bodies and permitting requirements that would need to be addressed. And Tech Memo 2 talks about all of this and the time required to get through that process. With that, I'm going to turn it over to Eric.
Thanks, Tom. Madam Chair, Eric Cheresia with Carollo Engineers. I'm going to briefly start by going over the basis of design for technical feasibility that was used as part of this study. The basis of design for technical feasibility is determined by several factors, including the potable reuse application, indirect potable reuse versus direct potable reuse, water quality and treatment needs, the treated water production capacity. For IPR alternatives, we also need to consider subsurface properties and hydrogeologic considerations. Must evaluate available project sites, project life, and reliability features. You can refer to TM3, where there's complete write-ups for each of these basis of design considerations, but I'm going to talk you through some of the major ones. For potable reuse applications, we considered groundwater replenishment by both surface and subsurface applications, in the Foothill Basin and Storage Unit 1. For direct potable reuse alternatives, we considered raw water supply augmentation to 3 places. First, we looked at augmenting the Cater Water Treatment Plant and sending advanced treated water to the Laurel Reservoir. We also looked at a dilution of the Charles Meyer Desalination Plant to lower the salinity and treat it there. And we also looked at creating a new water treatment plant, a membrane plant that would treat advanced treated water and then go into the distribution system. Tom touched on regulations associated with water quality and treatment requirements. For IPR, our groundwater replenishment by surface application or spreading, we considered tertiary treated water. For the groundwater replenishment by subsurface application, as required in the regulations, we considered a full advanced treatment train. Using the assumptions that Tom mentioned for direct potable reuse in our raw water supply augmentation schemes, we assumed a 14-12-12 log reduction. We considered engineered storage with 4 hours of storage time. And we also incorporated enhanced monitoring systems in the process. The target production capacity is specified in the work plans, which were approved in Workshop 1. The yield was based on the city's permitted desalination plant capacity, which is 10,000 acre-feet a year. However, it's important to note that the city also produces 1,400 acre-feet a year of non-potable reuse water. And since this is already considered in the city's water supply portfolio, any of these potable reuse alternatives cannot impact this non-potable reuse production. So taking that into consideration, all of our alternatives considered, the combined potable reuse and non-potable reuse production capacity must be the summation, which is 11,400 acre-feet a year. To look at how much wastewater was available from the city's Estero wastewater treatment plant, we did a flow characterization where we looked at the annual daily and hourly flows over a historical time frame. This graph that I'm presenting shows the Estero wastewater treatment plant daily secondary effluent flows from January of 2003 up until January of 2016. You'll note there's a range of flows from the minimum of 4.25 million gallons per day, or MGD, and the maximum of 26.5 MGD. However, the average is pretty consistent, and the average daily flow was noted at 7.73 MGD. I'd like to point out, in recent years, due to the historic drought that Joshua had mentioned in the introduction, the effluent flows have actually, you can see a pretty steady decline here in recent years. However, for our study, we use the average, to design our facilities, we use the average daily flow over that 13-year period. To give an idea of the treatment facility design, we wanted to know, it's important when you're designing a facility to not have any stranded acids. You don't want to build the facility too large where you're stranding your assets, and you don't want to build the facility too small so that you're wasting any water. So we did a statistical analysis using a percent not exceeded graph on the flows over that 13-year period, and we found, you can look at the 10% percent not exceeded to the 90%. The flows were pretty tight, which give us a confidence in our design that the average daily flow was a good metric to use. And this 8,660 acre-feet a year is the translation of MGD to acre-feet a year, which that number will come back later in our design, so I just want to highlight that. It's also important to consider that the wastewater treatment plant flows are diurnal in nature and that they fluctuate throughout the time of the day. This graph shows hourly flows over that same period of time, and you can see the diurnal variation here. We did an analysis based on this diurnal variation to determine the equalization storage that would be needed for the advanced water treatment facility. Because the membrane processes, the reverse osmosis systems, they can't accept a variation in flow. They must have a steady flow. So you must equalize the flow coming in with storage. Based on calculations, we determined that the equalization storage of 1.5 million gallons was necessary. Going back to the indirect potable reuse alternatives, it was important to consider subsurface and hydrogeologic properties. And these were determined basically by two methods, literature review of existing data for the area, and also an evaluation of analysis inputs from the Santa Barbara draft flow and transport model, which was developed by the USGS, which I'll touch on in greater detail later in the presentation. But this is how we were able to obtain certain characteristics like injection rates, percolation volumes, and groundwater recharge and discharge rates. Looking deeper into the IPR alternatives, we actually considered two indirect potable reuse alternatives. This figure shows an overview of IPR alternative number 1, in which surface and subsurface applications, so spreading and injection wells of this advanced treated recycled water in the upgraded portions of the foothill basin here and in storage unit 1. And this figure shows the locations of the conceptual private production wells, the added IPR recovery wells, and the injection wells. And I'd urge anyone to go look deeper at this figure and the explanations that are in TM3. Additionally, we considered IPR alternative number 2, which was actually the subsurface application or injection of the recycled water to create a seawater intrusion barrier. You can see that here along East Cabrillo Boulevard. It was determined through our analysis that even with 24 wells, that the barrier was ineffective at preventing seawater intrusion, so it was later discounted from further study. With that, I'm going to dive into a little detail about the hydrogeologic modeling analysis that was performed to look deeper at the IPR alternatives. Central to the evaluation approach was the use of the draft Santa Barbara groundwater flow and transport model, which was prepared by the USGS and developed for the city's long-term water supply program. And our key analysis involved an iterative approach for both of our implementation approaches, where we increased groundwater replenishment rates with and without IPR recovery pumping until certain constraints couldn't be met. And these constraints include the travel time requirements that Tom mentioned previously, along with various other constraints such as creating artesian conditions. And all these are laid out in TM3. This table presents some results from the modeling efforts. You can see results for both surface application and injection for the storage unit 1 and foothills basin. Unfortunately, without increased pumping, the recharge volumes are limited. You can see over the analysis period, the average was only 250 acre-feet a year. However, these recharge volumes increased with pumping. When you combine surface application and injection over the storage unit 1 and foothills basin, there was an average of about 8,500 acre-feet a year that could be deemed. And bringing that back to our wastewater treatment analysis, the available, again, as I mentioned previously, was 8660. The membrane process, the RO process that's used to treat the advanced treat the water, uses an RO system that we assumed an 80% recovery. So we only have about 6,928 acre-feet a year to inject. Bringing the modeling further, we also evaluated other impacts, such as the impact to sensitive habitats and shallow groundwater contamination. It was found that groundwater replenishment by surface application had the potential to increase groundwater levels that would impact sensitive vegetation, could create riparian or wetland areas, and could also cause changes of water quality in existing areas. A good amount of the recharge areas that were analyzed in the study were coincident with sensitive habitat areas. Furthermore, it's noted that the groundwater replenishment by surface application may mobilize shallow aquifer contamination. Additionally, it was noted that surface application could increase the risk of geologic hazards, such as liquefaction, which are affected by rising water levels in head. Some of the reaches used for surface application were coincident with hazard areas, which may cause slope failure. And finally, the higher groundwater that would result from a surface application in the shallow zone could cause moisture intrusion in foundations and could increase buoyancy forces that, again, could increase some of the structures that were built on those areas. So the negative effects that I just mentioned made surface application not feasible. This table presents an updated modeling analysis that we performed in which we did not use surface application. You'll note that the total recycled water recharge to both basins averaged about 7715 acre-feet a year. Bringing back to the available raw water that could be used for IPR of 6928, it was determined that all of this water, could be brought for an IPR process. So after we went through all these bases for technical feasibility evaluation, it was possible to summarize various potable reuse alternatives. We ended up with 6 alternatives which optimize contributions to non-potable reuse, which the city already practices, indirect potable reuse, and direct potable reuse. These 6 alternatives, you can see alternative 1 at first maximizes NPR treatment, and then any additional flow that's left over would be used for DPR at the Cater Water Treatment Plant. Alternative 1B just maximizes DPR at the Cater Water Treatment Plant. Similarly, as 1A and 1B, 2A and 2B maximize and then minimize NPR, but then instead of going to Cater, they use the new water treatment plant for DPR. And finally, alternative 3A and 3B consider IPR treatment, in which in alternative 3A, you first maximize non-potable reuse, and then use the remaining flow for indirect potable reuse. And then alternative 3B, in which you're just maximizing your IPR treatment. So now I'd like to draw your attention to our final summary of potable reuse alternatives. This is a handout, so if everyone could pull this out, I'm going to just talk through one of the alternatives. Alternative 1A, to kind of give an idea of how to read this figure and go over that. So starting with alternative 1A, you'll note that the Estero wastewater treatment plant is producing an average daily flow of 8,660 acre-feet a year. Now remember back to that alternative matrix, the alternative 1A maximizes NPR treatment first. So the 716 acre-feet a year goes, and that's the eastern flow of NPR that's currently planned for. That goes to an NPR treatment system, which has 100% recovery, and then goes to the east NPR distribution system, which includes future flows. The remainder of this flow, 7,944 acre-feet, goes to a DPR treatment train. And as I mentioned previously, the process is 80% efficient. So 80% of that flow becomes advanced treated water and then goes to the west NPR distribution system, which would be used to transmit the water to the Laurel Reservoir to ultimately be retreated at the Cater Water Treatment Plant. The remainder of this 20% is brine and must be disposed of. The description notes section of this figure shows that this option summarizes in words that maximizes NPR treatment and uses the Laurel Reservoir, where only tertiary treated flows are going east. However, all flows going west are DPR treated and sent to Laurel Reservoir. You'll notice that in that list of alternatives, back when I mentioned our alternatives, we were also considering a dilution of the intake at the Charles Meyer Desalination Plant. However, this was discounted after an initial analysis. The recovery of the desalination plant remains unchanged, so the intake water salinity at capacity only decreased from 34,000 to 25,000 milligrams per liter, which wasn't in the range where you could do an alternative process that would increase recovery. So the recovery of the plant still remained at 45%, which translates to a 55% loss of AWTF product water. So it was found that better utilization of the wastewater treatment effluent would be had with reusing the Cater water treatment plant or constructing a new water treatment plant. Next, I'm going to go into the details of the treatment processes that were selected for the potable reuse study. As mentioned previously, the city currently practices non-potable reuse, or NPR, and the secondary effluent is treated with microfiltration and chlorination. For this study, it was actually assumed that the NPR facilities would be relocated to the annex yard and would be incorporated into the new indirect potable reuse or direct potable reuse advanced water treatment facility. This would free up space at the Estero wastewater treatment site where it currently is, and would also consolidate the treatment equipment and the operations expertise. As Tom mentioned in the summary of regulations, the indirect potable reuse process is dictated by Title 22 requirements. I'm going to walk through a flow diagram of the IPR process in which secondary effluent from the Estero water treatment plant is brought to our equalization tanks that were, again, as I mentioned from our flow characterization, designed at 1.5 million gallons, then through a microfiltration system, a two-stage reverse osmosis system, and then a UV advanced oxidation process, where the water is ultimately brought to engineered storage, which was designed for 4 hours of retention time, and then to injection wells or spreading basins. The DPR process that was chosen for this study was based on the most recent regulatory activity and precedents in California. This train is very similar to the one that we just showed for indirect potable reuse. However, because of the additional treatment requirements that we're expecting with DPR, there's an additional disinfection step where you're using ultraviolet in between microfiltration and reverse osmosis. Also, this train has enhanced monitoring systems, online monitors and that sort of thing that were included in the design. So I'm going to walk through the conceptual design summary for all of the 6 alternatives that I mentioned and project descriptions. Again, I'd like to turn your attention to one of the handouts, which is for alternative 1A. It's a pipeline alignment. And I'm going to walk you through this alternative, but these similar figures are given for each of the 6 alternatives, which kind of show the details of the design and any key design considerations. So we'll start here with the Estero water treatment plant, where there's a 16-inch pipeline that's constructed that goes to the DPR facility. Then, as mentioned previously, this alternative maximizes your non-potable reuse. So this existing east system remains and conveys tertiary treated water. However, the west system over here is repurposed and already goes to the golf course pump station and reservoir. Portion of this line is actually a little too small. It's a 12-inch pipeline. So for this strip, we would have to add a 12-inch parallel pipeline to allow your DPR capacity that we've added. But after this, it goes to a 16-inch line and then ultimately goes to this area. And then from the golf course pump station and reservoir, we'd add a new 16-inch pipeline that would ultimately convey the water to Laurel Canyon or Laurel Reservoir, where it would be retreated at the Cater water treatment plant. This table presents a summary of the potential maximum yields from each of the alternatives. You'll note that the table splits up your contributions from non-potable reuse, indirect potable reuse, direct potable reuse, and then sums up and gives you the total yield of each of these alternatives. Next, I'm going to touch on the conceptual design summary that was performed for the advanced water treatment facility. You've got in your handout several renderings of the AWTF that was designed and modeled in 3D rendering software and actually overlaid over a scaled image of the site. I'm going to talk through some of the major processes and try to go in order of how the water would come to the site. So first, from the Estero wastewater treatment plant, secondary effluent is conveyed to these equalization tanks. And each of these tanks is 1.5 million gallons to provide full redundancy for the tanks. From the tanks, the water flows to this MF pump station and wet well, where the feed pumps for the microfiltration system pump through the microfiltration system, and here's the microfiltration system, then go to the pre-RO UV system, then are conveyed through cartridge filters and through the reverse osmosis system. Well, after the reverse osmosis system, the water is then conveyed to the UV AOP system and then to the engineered storage tanks, which have been designed to provide a residence time of 4 hours. Ancillary facilities include a control room, electrical mechanical room, chemical storage and feed area, and a clean-in-place system for the membrane systems. With that, I'm going to turn it over to Tom, who's going to highlight the initial screening analysis and provide a summary of the study.
Thank you. So the potable reuse initial screening analysis included criteria that were identified in the work plan, including things like the geologic hazards, hydrologic factors for the IPR alternatives only, oceanographic factors, tsunami run-up, those sorts of things, presence of sensitive habitats, and design and construction constraints. So this process, the criteria were included in the work plan that was approved by the regional board. This table is a handout, and it presents the initial screening results for the various screening criteria. You'll see like geotechnical hazards, hydrologic factors, oceanographic factors. Within the table, we have defined the criteria as being potentially feasible, PF, and those cells are colored green in this handout. Potentially feasible, but not currently meeting the study goals. Those are PF stars. And those are things that when the city updates their long-term water supply plan and they want to change what the study goals are, those are things that can be addressed through that future update. The two yellow-colored PFs or orange-colored PF stars on this graph relate to the 10,000 acre-foot capacity element, or the 11,400 capacity element for the alternatives 3A and 3B for IPR. So that basically meaning that the IPR couldn't receive that quantity of water. With the next side of this table, in the next page, we have the screening criteria for sensitive habitats and also the design and construction issues. And here again, we see the 10,000 acre foot popping up. And this is on the production side as opposed to the hydrologic factors being the groundwater basin not being able to receive them. So none of the alternatives met the production goal for 10,000 acre foot. But again, when the city updates their long-term water supply plan, the studies identified a lot of good information that can be used. That 10,000 acre foot criteria could be adjusted in the future. So none of the alternatives pass the technical feasibility screening process. We've also presented here whether or not there were regulations governing the process. So the direct potable reuse alternatives 1A or alternatives 1 and 2, there are no regulations for direct potable reuse yet. So in summary, we had none of the potable reuse alternatives met the study goals and survived this initial screening process. 4 of the alternatives passed all of the screening criteria except for the fact that they were limited in the availability of effluent from El Estero to produce the 10,000 acre foot or the 11,400 acre foot production goal. The IPR alternatives also failed additional criteria related to whether or not the groundwater basins could receive that much water. So any alternative that's carried forward in the long-term water supply plan that might include IPR, there'd be other supply options needed to add up to 10,000 acre foot ultimately. We wanted to point out that there were several alternatives that were discounted from further study before the initial screening process, and those included use of the advanced treated water, product water for diluting intake water at the Charles Meyer desal plant. And again, that was because the dilution was not significant enough to change the recovery rate of that process and would result in a large loss of this advanced treated wastewater. There was an IPR alternative 2 that was discussed in Tech Memo 3 related to creating a seawater intrusion barrier, and the hydrologic modeling that the USGS conducted showed, and that GSI was working with too, it showed that the seawater intrusion barrier was not effective. IPR by surface application was also discounted, and as Eric had summarized, that was because of the potential hazards that were created with liquefaction, slope failure due to the high groundwater levels. There's also potential to mobilize groundwater contamination in the areas where those surface spreading zones were interconnected with the surficial groundwater areas. So it wouldn't only be recharging the lower production zone where the city's groundwater wells are producing from. There's an upper confined aquifer that there is known contamination in that could be mobilized, as well impact to sensitive habitats. So I'll turn it back to Joshua.
Okay. I'm sorry, Joshua.
Just wanted to just basically wrap up here and summarize. This wasn't a wasted effort. There was a lot of information gathered here that I think is going to be invaluable to the city's long-term water supply plan update. And unfortunately, we do have to wait. We are in an emergency right now. Doing planning during emergency is awfully difficult. Staff are spread thin, and it's difficult to know what we're exactly planning for when we're still trying to deal with an emergency. And so, with that said, concluding this drought, and hopefully will end soon, will allow us to reassess where we stand with our surface water supplies, which we know are changing dramatically, potentially with the new drought of record, or with the new drought of record. And so we're also waiting to see how the biological opinion comes out for Kachuma, and potentially that could have adverse impacts on supplies from Kachuma as well. And also reassessing the safe yield from the Kachuma project. We expect that could go down dramatically. And so with that, when we begin the long-term water supply plan, we will know exactly what volume we are looking for from this new supply. And I think that would allow us to be much more surgical, going back to using this data and assessing what we need, whether it's from desal or from potable reuse, and how we might move forward. So with that, that concludes our presentation.
Oh, thank you very much, Joshua and Tom and Eric, for the presentation. So the next agenda item is going to be an opportunity for the panel members to ask questions of the project team. But I do want to mention to the public, for the public comments, if you fill out a comment card and give it to me, then we'll be ready for the public comments after this next agenda item. Amy, can I turn it over to you for panel comments, questions?
Yes. And I'd like to open it up to the panel for questions.
Actually, I'd like to, I guess, make more of a comment than a question. I'm assuming that Carollo and the city are aware that even in the absence of adopted regulations for DPR, that DDW has indicated that they have the authority and have expressed the willingness to evaluate projects on a case-by-case basis for DPR. So it is possible to do it. That's not really a fatal flaw, the absence of existing regulations. So it's possible to move forward with a project. It wouldn't be easy, though, because we did it before there were final groundwater regulations, and it will provide probably a greater body of evidence to substantiate why what you're proposing will be considered adequate when they have finally regulations in place. But the process of DDW evaluating case-by-case projects for direct potable will actually help them to inform when they do actually start to try to adopt final regulations. And that's basically what happened with groundwater recharge regulations. Projects like ours and others were actually helpful for the process of them adopting final regulations.
Great, thanks. So can you explain more? I'm just curious why the RO recovery is limited to 45%.
On the seawater process?
Yeah.
Okay, so the seawater process is like the brackish water process in that you're limited by salt saturation, sparingly soluble salts that could concentrate to the point where you're going to form mineral scale on the membranes. Certainly, it stands to reason that diluting the intake water could benefit the salt saturation, but the types of salts that we're contributing aren't proportional with this diluted water. So we have some concerns about scaling as well. The to increase the recovery rate on the existing seawater system, you'd have to add another stage to the process. So we're limited by the current configuration. Certainly, we could add more facilities to treat more brine in the absence of this concern over the scaling potential. The net benefit in terms of the payback for squeezing out that additional water is usually pretty limited. So usually you don't see seawater systems trying to increase recovery rates beyond 45% is typical because of the energy recovery technology that is most efficient. There are some older energy recovery technologies where you'd see seawater processes with a little higher recovery rates, maybe 50 or 55%, but those systems did struggle with fouling of scales or particles, things like that, because it changes the hydraulics of how the system operates. It's a very technical answer to your question. So
Okay. At some point, it would start to look more like a brackish system, though, than a seawater system. Right?
It would. And with the current seawater systems, while the energy recovery, you're using less energy at the lower recovery rates, you are drawing in more seawater to meet that lower recovery and the more energy efficient operation. So there is some balance that needs to be played with regard to intake volume and energy use. So we were able. The existing plant design was at 45%. So we haven't changed that. We have updated the energy recovery technology to be this more modern version of the technology. So we are seeing the benefits of that. I'm not sure how else.
That's good. Okay.
If I could ask another question. The flip side, now go back to the potable reuse, the 80% recovery. for a two-stage RO system, where did you derive that number from? There's many places in the world where they're using a 75% recovery assumption on a two-stage system. We have a three-stage system, and we get a little less than 85% recovery. So it looks as though 80% is a pretty confident, pretty optimistic assumption about recovery with a two-stage RO system. Are there enough places you were able to draw on, use as examples to assume that you'd be able to achieve that?
Yeah. So California experience has been, as you said, ranging from this 75 to the 85% rate, with the 85% systems tending to struggle more in terms of the maintenance issues.
Typically three-stage.
So the three-stage system that you have should really be a two-stage system. So
There's lots of people who have talked about that.
Right. The hydraulics of what you need staging-wise, if you're going to increase recovery past 85%, you need a three-stage system. So for what you guys are doing, it should really be a two-stage system. You'd have better internal hydraulic conditions that would actually result in less maintenance.
We can get in a detailed discussion. With the new expansion of the plant. We actually have
Yeah.
better interstage controls, and so
Right.
we actually are, I think, have a better system to operate at three-stage. The earlier system, you're right, would have been better as a two-stage system, or just make lower recovery assumptions.
Yeah. So I guess, to answer your question, we looked at California experience, knowing that what the limitations were on those systems that struggled at the higher recovery rates. We chose the two-stage system as.
But you're making pretty confident recovery assumptions for a two-stage system at 80%.
I wouldn't say that they're unwarranted. That there are successful IPR or advanced treated RO systems out there operating with two stages at 80% and doing so with not the maintenance issues that have been seen at those systems with higher recoveries and three stages, or even those systems that have three stages and operating at lower recoveries.
And the feed waters are basically comparable.
The feed water, it's always hard when you're dealing with surface water or advanced or secondary effluent, where the quality changes and things like drought. We would, moving on to a pre-design level, probably have some range of recovery that would be represented, so that you could turn a dial that if, say that the water quality, the mineral content worsens during a drought, or there's some infiltration event that out in the collection system that changes the mineral content significantly, that dial could be turned. And that certainly needs to be addressed with respect to the nameplate types of numbers that we've been showing here as that dial is turned. So while the 8660 available effluent represents a average nameplate production rate, there does need to be some reduction level of safety factor worked in as the city would potentially move forward with something like this.
For both the online factor as well as the recovery.
Yeah.
So it's hard to know where feasibility stops and practicality starts. But for the APR with concurrent pumping, so you're basically going to turn the whole entire basin into a giant environmental buffer, and you would have to have a continuous put and take operation. So the question then becomes, what do you do with the other water resources in the portfolio? You would have to continuously pump the basin and continually inject. So what do you do with water from Kachuma, which would be cheaper?
That would be a challenge, and that's the part of that is, that water would remain in the lake, would be subject to evaporation, And
Somewhat.
you're constantly balancing that. You could sell it, and I think we'd be kind of balancing that portfolio. What I think we've presented here is kind of the maximum, and I think that's why when we really came down to it, we'd want to be somewhat surgical about it. I mean, ending up with an enormous amount of water in Kachuma that goes unused is not necessarily the end game either. It's kind of balancing that, making sure that we have a diverse portfolio. I think the technical study here is just trying to establish potentially a maximum yield out of this. I looking at the challenges of how much property that would take and the other technical feasibility that you're aware of.
Bring that up because it's feasibility.
Right. Yeah, it's exactly. It's feasible. I think that it would all need to be taken into consideration with the impacts to our other supplies. Yes.
I want to ask a related question then. And maybe it's just clarifying that looking forward, you would look at changing operations potentially of existing systems so that you could do a inject withdrawal at a limited capacity because you're constrained by your basin, but consider changing the function that Kachuma plays in your water supply portfolio. In other words, perhaps that becomes your drought supply and you're on and off your basin more frequently.
Absolutely. I think all that needs to be taken into consideration. And what we're looking at just even currently with desal, because it's going to be coming from relatively the same spot in the city, which is the bottom half of the city, is how exactly do we distribute all of that water? And really coming up with a long-term plan that if the future is some portion of desal and potable reuse, and it's all coming into the bottom of the city, how do we get it to all the other parts of the city, which some are kind of limited to only getting surface water right now just based on how the system was initially designed. And so I think all that would have to be taken into consideration and trying to strategize what Kachuma's role is going to be surface water-wise.
When you calculated your average daily flow for wastewater and you picked up the final years, the most recent drought years, and I'm just wondering, looking forward, are you anticipating any kind of recovery that would have an impact on that average daily flow? Or to be conservative, are you maintaining and going to include those lower production years in your average daily flow?
I think in water supply planning, we would include that kind of cushion, and we know that the basin does have a safe yield already existing in it, and so that would act as some type of buffer when we didn't have the available water to inject. I can't say that I mean, I appreciate having these probably higher end numbers, but I think for long-term planning, we'd probably assume something much more conservative.
And then along those lines, the 1,400 acre feet per year that's existing NPR water use, I don't know what the climate's like here, but where I'm from, we can discount that in the wintertime so that that's not part of that calculation for needed source water. And I'm wondering if that's similar here, or do you have to rely on that as a full year volume to your customers?
That's a challenge for us. Is obviously during the summer months, there's about 6 months out of the year when we get the majority of our non-potable reuse demand. That represents kind of our year-over-year demand, but it peaks in the summer when we have to provide, at times, 2.5 million gallons a day of recycled water to those customers. But trying to figure out how to feed that in if we were to move away from a non-potable source, maybe basically putting these people back all on potable water. Obviously, that has its challenges fundamentally, but when we talk about having water for higher purpose, and if that water is truly available with, I would say, minimal treatment costs, I think it's worth revisiting whether we still want to operate a non-potable system, which has with it a whole bunch of restraints and concerns in the community, if the possibility of potable reuse is available to us.
Our agency engages in that debate whether we maintain our non-potable system or convert everything over to potable. So it's not unique to Santa Barbara. That's an ongoing debate. Can I ask a related question on the groundwater basin to what Heidi asked about a moment ago? You have a yield in the groundwater basin as it's operated now, and you assume based on the USGS model that the seawater barrier would not be effective. Now, what are the assumptions made about the condition of the groundwater basin where the seawater barrier is not effective in preventing seawater intrusion, or not giving you at least greater flexibility in terms of how you can operate the groundwater basin if you had, in fact, a seawater barrier injecting on a continuous basis.
We're going to let GSI answer this one.
Thank you. Jeff Berry with GSI. The modeling that was performed was done under the assumption that historical climate would be repeated in the future. So we took a period of time where we had historic low rainfall conditions and normal, and then higher rainfall conditions, and then assumed that would repeat in the future. So during those periods of time when we had low rainfall conditions, we had maximum pumping going on in the basin with the city's existing wells to supply the potable water needs. And it was during those times that we were also looking at the effectiveness of the barrier when you had the maximum pumping going on in the basin, as we see now. So we looked at the feasibility of the barrier with the injection of IPR water during the full range of climatic conditions, including drought conditions that we've seen historically.
So it wasn't seen as providing you greater flexibility in terms of the range of conditions you'd operate the groundwater basin under if you had a relatively reliable source of fresh water in between the sea and the groundwater basin.
Yeah, unfortunately, in the location where we would want to do the injection for the saltwater barrier, the sediments out there, the aquifer conditions are pretty poor, and so we couldn't get enough water in the ground, because also groundwater levels are quite high generally at that location. It's not like it is the case inland where you have depressed groundwater levels due to where all the pumping is occurring. Out on the coast, yes, water levels are declining and sometimes below sea level, but there just isn't enough room to even inject to maintain our constraints about water levels in the injection wells above surface.
So it's physical limitations based on the aquifers.
That's right.
It's just the inverse of when they're trying to get seawater out, I mean, in the previous analysis. So.
Thanks.
In your in the analysis on flows from the wastewater treatment plant, you calculated the historic flows. Heidi mentioned you're going to look at sort of the dip and what happens and how does that get calculated into your planning. Let's think about the reverse is true. You're trying to solve a problem for 10,000 acre-foot of desal for which you're not serving today. In the future, you'll be serving a lot more water. You'll have a lot more wastewater. Did you give any consideration to the future wastewater flows as a result of increased in potable use?
We did briefly discuss that, and I think that's kind of why we chose to go with the numbers that we have right now, which assume what I'd be more optimistic at this time. But if you were to add in population growth, I mean, we're currently seeing less water coming into our wastewater treatment plant. I would expect some of that to be hardened and not necessarily come back when rainfall comes back. People are changing out home appliances and things like that. So I think for the kind of the general planning horizon, we felt like the 8660 that we used was kind of a hybrid for the time being.
Talk about your demand, and we've had a hard time getting you to talk about demand in this process. Mm-hmm. The 10,000 is meant to replace a permitted facility, but we're not sure what you're serving with the facility. What would your demand be? What would you be serving by the time you've reached 10,000 acre-foot use of the desal plant? Would it be more than you're serving today?
At this time, I mean, it's a combination of it's reserving that capacity should we lose Gibraltar, which is filling in with sediment, should we lose significant capacity, and then there's also the regional benefits of a facility of that type. So this water may be used to help meet some of our regional neighbors' water needs as well, kind of trying to create some sustainability to our region.
So no future wastewater flows were considered as population increases and there's more wastewater flows. You've left those off the table to consider for the future use.
Correct, and I'd add to it, in 2010, our community was producing on average about 8 MGD, and going back further, it was closer to 10 MGD, and so we've seen this steady decline despite modest population growth. We've continued to see this steady decline. Same solids coming into the facility; those seem to be staying fairly flat. But the amount of water that's coming in with those solids seems to be getting with changes in indoor water usage. So.
One more quick question. On your slide 38, it was the slide where you showed the different alternatives. You talked about maximizing NPR at 716 in alternative 1A, but then you talk about maximizing NPR at 1400 in 2A and 3A. Mm-hmm. Maximizing 700 or is maximizing 14?
This is somewhat confusing. What is in 1A was basically splitting our recycled water system. There is a recycled water system that, for all intents and purposes, heads towards Montecito. And then there's a recycled water system that heads west up to our golf course. Under this scenario, we said that we would continue to operate the recycled water system going towards Montecito and Montecito Country Club, but we would be repurposing all the piping that goes the other way. And so that's where we came up with this kind of a hybrid solution. I have issues with, if we're either going to be into recycled water or we're going to get out of the recycled water business. But this was intended to try and show some type of a hybrid and reuse of existing piping. Does that answer your question? It's maximizing it to a portion of the city. We'd maximize NPR.
Different maximizing.
Yes, yes.
And you've introduced the term NPR here. I didn't see this term earlier. Did I miss this introduction of NPR? Because we've been talking about IPR and DPR, and then you slip into this slide and you talk about NPR, DPR, IPR. Is this 1400? Is this what we're getting at? Is your existing?
That is our
on the tertiary treated, and everything else is going to advanced treated. That's when you move to the IPR, DPR. Is that the distinction you're making here?
That's correct. Yeah.
It sounds like you subscribe to a drought theory versus a drying climate, and how that's affected your projections.
Quite understand. The drought. Well, I think there will be an end to this drought, but I think the idea that you're right, that the climate is changing and we should be planning for drier stretches of time, I think are going to be a reality with our supply planning. And that's exactly what we'll be looking at with the safe yields of our surface water supplies. One of the things that technical panel may not be aware of, we had recently a significant fire in the backcountry. It burned a big portion of our watershed above Gibraltar, which is a city-owned surface water reservoir. And, just got back from a bear report on that, and roughly they're expecting about 500 acre-feet of sediment to come into that reservoir, which at its full capacity was 14,000 acre-feet, and now we're at about 5,200, and with this additional sediment, that reservoir just continues to decrease in capacity, and at some point will basically be just whatever we can hold above the gates. It won't be much. And then that sediment that we've been holding back now gets moved on to Cachuma. And Cachuma will actually start to see some of the full impacts of the sediment that makes its way down the San Ynez River.
We're looking at the table 3.19. You showed a table like it on the screen where you showed the maximum potential yields of the alternatives. You had the NPR, IPR, DPR. This slide. In the document, you put the desal yield in here as well. And you make the point that in alternatives 2A and 2B, you lose desal capacity because you need to take space at the desal plant. Expansion of the plant to 10,000, not internal to the plant, you take up a larger footprint, so the site is no longer, or is it outside the footprint, so the site becomes not available for desal if you use that property for recycle treatment?
So we put that in there because it would render the site incapable of reaching that full 10,000 acre feet. And so it was discussed in the report that in order to site this basically surface water treatment plant, this would be your engineered barrier, or second engineered barrier would require space located if you don't use Cater nearby, and that would take up space that would be basically another 5,000 acre feet of desal production.
Right, because you say in the report in section 325, you'd look at new treatment facilities at a portion of the Charles Meyer plant site or at the your city yard.
Mm-hmm.
Don't mention there that you'd have to take up some of the desal plant space site. You'd said you'd take up the site, but in fact, you would have to not build out the desal plant in order to use that parcel on the site?
Correct.
And the desal plant, the yard piping, the piping in and out of that plant site is specifically designed to get you to that 10,000?
That's correct.
So you'd actually be giving up some of that capacity. Some of that capacity would be stranded if you had to reduce the output of the plant.
Right. We've sized the intake structures and piping to go all the way up to 10,000. So yes, we'd be giving up that excess capacity.
And I want to add to Eric's question about that table. It's similar to this, but in the report you show the total where you add in the desal capacity, and that total yield is just for demonstrating a reduction in the desal capacity as opposed to being used as any kind of comparative volume of alternatives.
Right. No, it was just to show that there would be, when you're doing that, you're limiting the capacity from desal. That was what it was meant to show.
Not because you need that total right-hand column. Just
That's
to demonstrate,
correct.
because in order to find that you could lose the reduction, you've got to find that little paragraph stuck in 2A.
Okay.
Right? Okay. Got
Good.
it.
Thanks.
All right, good. Any more questions from the panel? Okay, we're going to take a 5-minute break.
We don't have that many public comments.
Okay, then we'll proceed.
We have 2 so far,
Okay.
so we might be able to get through them.
Okay, good.
Okay, so the first public comment is from Kara Redmond.
Good morning. I'm Kira Redmond, Executive Director of Santa Barbara Channel Keeper. I'd like to repeat for the record that by defining feasible as capable of producing 10,000 acre feet, these studies are a grave disappointment and disservice to the ratepayers of Santa Barbara. By setting the threshold for feasibility at 10,000 acre feet, more than 3 times the amount of water the city is now recommissioning its desal plant to produce, the findings that subsurface intakes and potable reuse are infeasible were premeditated. This was done deliberately in order to justify the city's continued pursuit of desal with an open ocean intake, which we all know will have significant adverse environmental impacts. My takeaway from these studies, which is what I will relay to reporters and ratepayers when I talk to them about them, is that both subsurface intakes and potable reuse are in fact likely feasible and capable of producing at least twice as much water as the city intends to produce with an open ocean intake desal, with significantly less environmental impacts. Yet, despite these findings, the city is proceeding full speed ahead with the most environmentally destructive option. Hopefully, when the rains return or the city's leadership changes, this information in these studies will be used to develop a more sustainable water supply portfolio for the city of Santa Barbara. Thank you.
Thank you. And the second comment is from Hillary Hauser.
Hillary Hauser from Heal the Ocean. Thank you very much. Excuse all the whispering back there. My assistant, Alex Bennett, was telling me where we are. I was late here. Thank you. Heal the Ocean's been very involved in recycled water. We've been before the panel before to advocate moving forward with both. We have just submitted our comment to the State Board on DPR, and since their plan is kind of very long-term, we said we think the wastewater treatment plant should proceed with what they can proceed with now while DPR is so way off, but yet build infrastructure that DPR can be added later. We would say the same thing with the long-term plan here, is that while we work on that long-term plan, can we not, purple pipes are tried and true, and everybody doesn't want to do that, but is there a manner to capitalize on alternative 2A 1400 AFY now and 5808 DPR later, or 3A, which is 1400 now and 5808 AFY IPR later. And so, because, I mean, even though the conservation has brought down the use of water dramatically for irrigation, it's still a big, big, big use of potable water. And also, we've got this fire situation that isn't so hot. So, and the other good thing about the NPR treatments, non-potable reuse treatment, there's no brine treatment that's necessary. And that's an issue, too, for the wastewater plant. Heliogen's working on a paper on brine treatment for CASA, the California Association of Sanitary Agencies, right now to deal with that because, anyway. So I would just like to say this work on the desal as we look at these charts for the alternatives, if we could just possibly get some infrastructure in now because the game has changed dramatically and in such a way that it can be added to later, recycle water. And then when we get to desal, maybe we won't need so much of it. Thank you.
Thank you.
Thank you very much. So I do want to ask if there are any other public comments at this time. Okay, thank you for those. I do want to mention.
Hang on, Jeff.
Excuse me, Jeff.
I'm sorry.
Just a comment on the two public comments. Both of you, I think, are expressing things that this committee has talked about before, and I don't think that we disagree with you. We're stuck in a very difficult situation trying to solve the current drought situation while we're stuck in a long-term planning discussion. So I think they're both worthy comments, and we have brought up the issue of 10,000 repeatedly with this group, and whether or not we can move ahead with incremental implementation of projects while they're trying to solve the drought situation is putting the city in a really difficult spot. This has been a difficult panel, at least for me, struggling with the same issues that you both are struggling with here. It's a drought situation, but there's long-term planning output that will come out of this. When does that come together? Is that true and is that genuine? That's yet to be seen, but thank you both for the comments.
Okay, thank you. So I do want to mention that as before, we are taking written comments for another week after this meeting. So between now and I guess midnight on November 2nd, we'll be taking comments from the public. So just in terms of where we're moving on from here, as you know, the panel is going to continue its discussions while we're in town in terms of preparing a panel report back to the city and the project team. So that will be underway. I don't have a specific schedule for that, but we normally try to do those in the matter of weeks. And as part of that, there'll be responses to public comments. So Joshua and Tom, I just want to check in with you if there's anything else you'd want to say at this point. Okay. Thank you for the presentations, all the information, and the public, thank you for attending. Amy, are we okay to adjourn?
Yes, thank you.
Thank you.